Hello and welcome. My name is Sean Lacey of Lacey Maths and Stats Consultancy, and this video is a demonstration on using power analysis in G-Power and RStudio with a focus on repeated measures ANOVA. Similar to my previous video up on YouTube in relation to power analysis using G-Power and RStudio, which focus on t-tests, I'm going to approach this video using power analysis in three ways. First, for a sample size calculation, so your basic calculation, and then for the profile plot, and then multiple profile plots. Now, in the previous video, when I focused on doing the power analysis from a paired t-test, we could see that the G-Power and the RStudio results mapped exactly. Here, for this one, we're going to find that there's going to be a very small variation. I suppose, ultimately, when you're looking at the test that we're going to focus on, which is the repeated measures, are more so between and within subjects design. There's a lot of moving parts to that, to the final calculation. So there's kind of be a knock-on effect to a rounding error. So we're going to find that when we do these calculations, some of the sample sizes will be the same, but some might be just different by one place. So on the grand scale of things, that's not too bad. But I suppose it's just because there's a lot actually going on when you start doing a between and within subjects design. ANOVA. So I'm going to use the data that I would have shown in a previous video. So I would have uploaded videos on assumptions around repeated measures ANOVA, and I would have focused on the three assumptions: the normality, homogeneity, variance, and sphericity, and then how to actually present those assumptions if you wanted to present them in an appendix or something like that. So I'm going to use the data that I had for these videos, and it's ultimately, when we ran off the analysis for this, I didn't focus on it for the video for these videos, but we ended up with a statistically insignificant result. But when you looked at the strength of the result was actually in the moderate category. So there would be kind of, I suppose, a slight motivation to potentially doing a power analysis to determine, look, what would you need to increase the sample size to in order to determine whether or not the difference that you observe is statistically significant. So I'm just going to first just go to the script that I would have used in those videos. So I'm just going to highlight all that script here. I suppose where that video kind of focuses up, actually maybe if I just kind of quickly just talk through it. So I just stated the variables. So the data behind the scenes here is where you're looking at participants' triglyceride levels over 5 time points, so over 4 months, from baseline to the end of 4 months. There were 16 participants, and you're looking at it with respect to gender. Was there a difference with respect to gender? There were 7 females and 9 males as far as I know. Okay, so that was the background information. We checked for normality first. Then we looked at kind of our descriptive statistics around normality. Homogeneity variance was the next thing we looked at using boxes M test. Then we looked at sphericity. Now, obviously, when it comes to sphericity, and this is line 44 here, we would have done the repeated measures ANOVA, so the between and within subjects design. But the video that didn't really focus on the result there was more focusing on sphericity. So that brings us to this part here, so the line 48. And then I just looked at it, I suppose, how do you maybe put all that information, all just the assumption information together and write it to Excel. So I'm just going to leave out that last bit here, writing it to Excel, and just kind of highlight this. And this should all work out okay. So what we could see here is that generally there wasn't a massive difference in triglyceride levels. I suppose you'd see here that males were marginally lower. So they are marginally lower. So we want to potentially see, look, how many do we actually need? What sample size do we need in order for the differences that we're observing here to be statistically significant? So that's kind of the idea to it. So if I close that down, so there's the data. Let's just open this guy up a small bit here. And here we have the results. Okay, so it's just giving us a bit of a warning here that they're unbalanced. And that makes sense because we had 7 females and 9 males. And if we look at this here, we can see ultimately when we look at the interaction effect between time and gender, so whether or not there's a difference in triglyceride levels over time with respect to gender, we can see that we have a statistically insignificant result. But when we look at the generalized partial eta squared, we can see that that difference is classified as a moderate difference. So potentially there will be motivation then maybe to do a power analysis for that. And I suppose that's what we want to try to do here. When it comes to doing a power analysis in G-Power, and what I'll just do is just set it up, and we'll find that we're going to need another statistic. So if we look at the test family, we want the F-test family statistical test. We're going to look at the between and within. So the last video, the feedback on that was quite positive. The t-test video, I felt just doing a power analysis on a kind of a one-way ANOVA would nearly be just too straightforward, that I felt that maybe just looking at something a small bit more complex, like a within and between interaction, so your between and within subject design, would be kind of a one maybe more worthy of the video. So that's the one we're going to focus on, which is quite a challenging one. We're going to do the power analysis where we're going to look at the sample size. There's different types of, I suppose the first thing is look what the effect size would be. So what we can see here is for the effect size, we actually need it to be Cohen's F is what we need. When you look at the output that we have in RStudio there, we can see that we're getting the generalized eta squared. So we want to kind of look at that a small bit. That's going to be a small issue. Then it's a case of there's different options to how Cohen's F is calculated. Depends on whether or not with the partial eta squared, which is kind of a prerequisite to it, whether or not the correlation among repeated measures is included or not, or that calculation. So more often not, so if I come down here to options, more often not when I'm doing this, I would actually use the format that is in SPSS. Now, it's not that we're using SPSS for this, but generally I find that most statistical packages will present the partial eta squared that will be as in SPSS. So I'm going to use this format here. When we use this format, we're going to see that correlation aspect. Actually, I'll just go back to that a second. Here you can see, look, that it's expecting this correlation. So we can just see if we use as in SPSS, it's not needing that correlation anymore. Okay, but I suppose the reason I just wanted to look at this G power here is we actually need the effect size to be Cohen's F. Okay, if you want to use it in G power, and that actually is going to be the same when you want to do the power analysis in RStudio as well, using the particular function. I'm going to explain that now in a few minutes, but we're going to actually need it to be Cohen's F. Okay, so there's a small bit of prep work before we actually can go off and use G power here in this case. Okay, so we come back here to the script. I'll just enlarge that a small bit. So here we have, I'm just skipping those few lines. This bit here is just how we might present the assumptions. That was the focus of the previous video. Actually, so what I'm going to do, I have res 1. I've run off res 1. I'm going to just highlight that here. Okay, so when it comes to res 1, we have this output. So it's a nice kind of, I suppose, tidy output, which it gives you the p-values, whether or not, I suppose, ultimately in the middle, the sphericity is assumed. If sphericity is assumed, you kind of read the output up. If sphericity is not assumed, you kind of go down. That's fine, okay? Now, I came across a nice, I suppose, function on, I'm just going to show it here on, I suppose, trying to work out Cohen's F if you know different effect size, which is basically using this SJ stats library, and within that I'm going to use this ANOVA stats function. But to use that, what you actually require for that is actually the ANOVA table, that kind of output. So up here in the video, when I did the one about the assumptions, I just basically ran off, so this is line 44 here, I ran off the basic between and within subjects design. As an additional part to that script, I'm asking R to return an ANOVA table, so the AOV part, I'm asking it to return that for true. Now the reason I want that is not necessarily to focus on the results, but that just helps in using this SJ stats library, and more so into using this ANOVA stats function. So you can kind of, maybe when you kind of get to the output, you'll see, look, why we're actually just doing this additional step. So I'm just running off the the ANOVA again. That's the ANOVA. We get this ANOVA. So if I enlarge this a small bit, we can see up here we have the, I suppose we have the sphericity, we have the, or ANOVA results, so to speak, and then down below, then we're actually going to have this AOV results. Okay, so this is what we actually need in order to use this new function. Okay, so I'm going to just go down to that. Sorry there, let me scroll, make this guy bigger here. Okay, so just ran off that to get the additional bit, and then I'm going to load the library SJ stats. I put in the link there, you can just see the link. Just you might find there's nice reading material on that might be of interest, just what's happening with SJ stats. There's a lot to it, as in not hard, there's just a lot of, I suppose, output available. You could actually just isolate Cohen's F by itself if you wanted to by using this. I wanted to comment it out because I actually felt the ANOVA stats output table was quite nice. So I just said, look, I might just kind of show you that and then isolate the Cohen's F it's myself then from that. So that's what this is. So if I do that here and just enlarge this a small bit, what this gives us then is it gives us our ANOVA results. So here we can see our sums of squares, our degrees of freedom, mean squared, the statistics, and so on like that. But then it gives all these different effect sizes. Okay, so it depends on which one you want to use. You have eta squared, you have partial eta squared, you have omega squared, partial omega squared, and if you keep going down, look, you have Cohen's F. So that's quite nice. So we get all these different effect size calculations. Now the reason we're going to this effort here is because if we want to use G power, we need it to be Cohen's F. That's what we actually required. Now we could click determine here and we need partial eta squared, either or. Okay, when we look at the EZ ANOVA function that we use there, it outputted the generalized eta squared, not partial eta squared. So either way, we needed to do something to actually give us the various eta, I suppose, effect size calculations. So that's what we're just trying to do here. Okay, so what we can see here for cones F. So if we focus on maybe at the interaction effect, so whether or not there's a, so if I just maybe go up to the, actually we have the output here. If you look at the interaction effect, so this line here, we can see here's our p-value 0.453. If you look at the classification, if you look at cones F, that is classified as a moderate difference. So maybe we want to increase the sample size for that. So I suppose there's obviously a few power analyses that we could do. I felt the one that might be just the most interesting one to do would actually be on the interaction effect. So that's why I'm just focusing on the gender and the time one here, okay? And so I want to isolate this cones F, so 0.258. So if I isolate that, that's what my next line here, line 71 does, and there we have it, 0.258, okay? So that's the result I want to take into G power here. So I'm going to do 0.258 here. So if I do 0.258, my alpha is going to be 0.05. The power I'm going to work for here is going to be 0.8, but we're going to do the graph similar to the previous video that I did in power analysis for the t-test. We're going to do a graph ranging where the power ranges from 0.6 up to 0.95. We have two groups because we have the males and females. Okay, so we have two groups. There's multiple measurements. We have 5 measurements. We have 5 time points. We want to change that. Then the non-sphericity correction. So this is whether or not sphericity was assumed. When you ran off the EZ ANOVA, we found that looking at the sphericity test that we actually sphericity was assumed, so we leave this correction of 1. If sphericity wasn't assumed, we'd go down to the greenhouse geyser or the Hunt-Felt results, and we'd find that there's a correction statistic there that we'd actually use, and that's what we put in here. Okay, so if we, at the moment anyway, if we press calculate here, we're going to come back with an answer of 48. Okay, so I'm just actually going to close down this effect size bit over there. We don't need that, and actually, sorry, here, close, just not to be distracting anyone. So we can see here that this is telling us that our total sample size, if we want the difference that we're observing here in this study with the triglyceride levels over the course of the 4 months with respect to males and females to be statistically significant, we'd need a total sample size of 48. Okay, so that's what G power is telling us. I'm going to look at trying to get the same result. Now, it will actually turn out to be the same result here, which is quite nicely, but when we do the other, I suppose, the profile plots, we won't necessarily have an exact mapping because of, I suppose, like I said, there's a lot of parts to actually getting to these statistics anyway. Okay, so 48 anyway. Okay, very good. So we're going to come down here. So we do this bit of a side to look at converting the effect size, but that works out quite nice. I feel that this table is quite nice here. The next thing then is actually to do our power analysis. Now, in the previous video that I did when I was doing the power analysis for the pair t-test, I would have used the PWR, sort of kind of the power package. I would have used that. That was quite nice. But when it comes to doing that for a kind of a general linear model, and more so for the between and within subjects design, there's no option for, I suppose, there's no option for the sphericity correction if that is something that you require. So there is no option for that. There's also no option for if you wanted to focus on the interaction effect, or maybe you want to focus on the between subject effect, or maybe you want to focus on the within subject effect. It doesn't differentiate between any of them. So even though it's quite a good function and it gives a lot of nice output, I actually found that using WP, which is wp.rmanova function, is actually just a bit nicer, okay, in this case. So this is using the web power library. I have a couple of links there. I said I'd state them if anyone wanted to do maybe some background reading on them. So these are just nice. I suppose the reason I like this, I'm just loading the library there, is why do I like this? The reason I ultimately like this is because I can put in the correction coefficient, the non-sphericity correction if I want to, which can be of interest, and I can specify what type of, I suppose, effect I'm trying to focus on. Okay, so if I kind of just talk through this, now you obviously can just do a question mark, as in search for the help wp.rmanova, and you kind of get more background information. But NG is how many groups you have, so this is 2, or what is NM is how many measurements you have, so we have 5 measurements. Then we're looking at the effect, so that's what F is. So I've just named it EFF up here, so EFF, and then the power we're working off is 0.8. The non-sphericity correction is 1, and here type is 2. Now, if I said type is 0, that's where I will be focusing on the between subjects effect. If I said type is 1, that's the within subjects effect, but I'm focusing on the power analysis for the interaction effect, so type is going to be equal to 2. If I run that off, I get this output here, so it's telling me my power, the alpha, non-correction, and so on, and it gives me this sample size. Now, what this sample size relates to is the sample size across all the time points. So if we want to, the fact that we're looking kind of at a paired, as in it's the repeated measures, we just need to kind of isolate that a small bit. So what you have to do here is, what is it called? It's called RStudio $n. Okay, so you need to divide it by how many time points you actually have, less 1 as in the degrees of freedom. So we have the 5 time points, so actually in here we're going to divide it by 4. and then plus how many groups do you actually have. So in this case here we have 2 groups, so we say +2. Okay, and when we run that off, it's going to give us kind of a decimal number. Okay, so it's very rarely going to give us a nice integer, so we're just going to round that up. So ceiling on that, and this is where we end up with, and we end up with 48. Okay, so 48, which is quite nice, the exact same as we got in G-Power. Okay, now the later calculations we're going to do in a few minutes won't give the exact mapping, but you can kind of see, look, we're on the right track here with using these 2 functions, I suppose, or using these 2 packages, G-Power and RStudio, to doing the power analysis. And obviously the bonus on using RStudio, and this is what I would have said in the previous videos, is obviously we have the script, we have the transparency for every option that we're selecting in this case. Okay, so that's where we are here with this. So if we think back to just the steps, so what I've done actually here is I'm nearly pairing them up. So I did the sample size calculation for G-Power, then I did the sample size calculation for RStudio. Now I'm going to just look at a profile plot for each one, and I pair them up just to kind of see how do they align and the slight difference in them, and then look at the multiple profile plots. Okay, so where are we here? We're going back here. So I'm going to just look at the XY plot. I'm going to leave it as a default 0.6 up to 0.95, going up in increments of 0.01. I think this is a nice kind of graphic to actually present. So this kind of complements, I suppose, the result that you have. So when you're doing a power analysis, obviously our result here is 48, but it's nice to kind of give, I suppose, look what happens to the left and to the right of 48 if you ended up having more people with the same effect size, or if you wanted to aim for a higher power, or what impact does it actually have. So it kind of gives this nice graph, and I think that's a nice kind of, I suppose, a complement to doing a power calculation. So then the whole thing is, well, if we can do this in G-Power, it would also be nice then to do this in RStudio. So here we do it in RStudio. So in the previous video that I have up on YouTube, the power analysis using the pair t-test, I would have talked through a lot of this script. This is actually very same script. What did I change? The only script that I actually changed is I used a different power function. That's all that actually really changed here, was the knock-on effect of the power function. Everything else actually stays the same as that previous script. And sure, obviously this is where we really like RStudio, because it does that whole repeatability is just really nice. So for those of you that might be haven't seen the previous one, I'll just quickly go through it. So we're setting up the power vector. We're looking at the start point 0.6, 0.95, and the end. The reason I'm just going them is that's what was in G-Power. The increments, that tells us how many points we have. So this tells us we have 35 points. If you look at the graph on G-Power, we'll actually see we have 36 because it's not counting the starting point here. So we obviously need to add in n+1. Then I create a vector called size, which will basically be all our sample size calculations. Then it's a for loop, because I want to do the power calculation 36 times. This is where we have the function. And the one additional bit that I would have put up is, I suppose, from different to last, is where I'm actually dividing by 4, adding 2 based on the calculation for how many do we kind of want at each of the time points. I don't round this up. I don't do the ceiling on it. You can, there's absolutely nothing wrong with that. I suppose the reason I just didn't do it is because G-Power doesn't do it, and I suppose I'm just trying to kind of get it to align as much as possible to the G-Power result, because I felt that that was a nice kind of attribute or to the previous video that we would have done. So I'm just going to run this off. Here we have all the results. So I've just kind of I suppose mapped the power readings to the size. Okay, so that's what it is. We'll come back to that actually first. I'm just going to generate the graph. So I first generate the graph. Like all my previous videos, I usually do these plots in 2 steps. Kind of do the plot by default, is in look what does it look like, and then I look at I suppose scaling the axes, labeling the axes correctly, and so on like that. So I'm just going to highlight all that, because if you watch my previous videos, you'll be well used to the approach that I do, and we end up with this kind of nice graph here, which if we go back to G-Power here, we can see that they're quite similar. Okay, quite similar. Now obviously we can't tell exactly, but there's going to be a small bit of variation in the sample size calculation. I'm going to look at that now in a second, but overall we can see that we're actually looking quite well in that case. Okay, so what I just want to show you here, just as the final bit then, is just how does it different. In my previous video, when I did this for the pair t-test, they mapped perfectly. G-Power and RStudio mapped perfectly. But there's a lot going on when you're doing a between and within subjects design. There's a lot of calculations to kind of get to the end result. So there's kind of a knock-on rounding error to this, and that's what we're going to see here when we look at these. Okay, but it's not a massive rounding error. It's basically going to be a difference of kind of 1 most of the times. Okay, so if I look at this and come here to the table. So if we I won't look at them all obviously. So if you look at the first 1.6, if we round this to the nearest integer, this will be rounded up, sorry, because you're thinking of it's basically participants you're counting here. This is telling us we'd have 33 participants. Well, actually, so is this one. Okay, so it's telling us we have the same number of participants. Now the decimal places are different. In the previous video I did, the decimal places were the same, but here there's obviously a bit of a variation. What will be another one? I'll just go down to the 10th one here, 0.69. So if we round that up, it's going to be 38. The 10th one here, 0.69. If we round that up, it's going to be 39. Okay, so you can see there that we're off by 1, but I've even found in G-Power that if I was doing a sample size calculation, we'll say on an independent t-test, and I used the same statistics and did it using an ANOVA, the ANOVA, I suppose, power analysis function in G-Power, there could be a difference of even 1 or 2 in that case as well, even within G-Power. So this kind of slight difference is common. And in this case here, we're only off by 1. And that's if you kind of scan through. Maybe if I just looked at one more, look at the 14th one here, we see 0.73, we're up, rounding that at 41, 0.73, we're rounding that at 42. When I say rounding, it's always rounding up because you're counting participants. So 42, so we're only off by 1 in that case, okay? The other thing with this then, what I did in the last video is just looked at the idea of the multiple profile plots, because the whole thing is when you increase your sample size, you're basing it on the fact that your means and standard deviations will be the same, but obviously your means and standard deviations might differ from your, let's say, your pilot study. So if they differ, then that has a knock-on effect to your effect size. So how does varying your effect size have, what impact does that have on your power calculation? So what I just did was 3 plots just to kind of highlight that. So I'm just going to come back, I'll go to the graph here, I'm going to change this to 3 plots here. It defaults then to using this effect size of 0.1 up to 0.05, so as in going up in increments of 0.05. So from the example that we have here, the effect size is 0.258. So what I'm going to just do here, as in this is just an illustration, I'm going to go from 0.248 and I'm going to go up in increments of 0.01 just so we can see it. I'll draw that plot. So yeah, that's perfect. That's what I was looking for. So 0.248, 0.258 is the effect size that we worked out here in that, I suppose, in completion so far, and then 0.268. Okay, so this is where I just think it's a nice kind of graphic, because this would then show that as when you go off and gather more data, you ideally hope that the new data will map similarly to your older data, but there can be a small bit of variation. So if there's a small bit of variation up or down, what impact does that actually have? And this is what this graph kind of shows. So then I suppose the final step then is, how do we get something similar in RStudio? So we come back to RStudio, and again, this is very similar to the script that I would have done in the previous video. I know I'm referencing the previous video a lot, but I think ultimately that's what you find when you kind of have something that works really well, that you just kind of follow on from that. So all that I really changed here, again, I just actually changed the power function. That was really it, and obviously just how I mapped out the sample size from that previous video. So maybe the previous video is a nice kind of introduction first, maybe to before doing this one, but sure, maybe this is quite straightforward as well. So what we're looking at here is we're looking at changing 2 things. We're looking at changing the power 36 times and the effect size 3 times. This is where we kind of need a nested for loop. So we look at just setting up the power vector, the start, finish, increments, how many points that will be, the effect size vector, the start, the end, how many increments, the increments, and then how many points that will be. Then I decided I'd set it up as a matrix this time, so each column in the matrix will be an effect size, I suppose, will relate to the sample size mapping to a particular effect size. So that's what I would have done here, just as a sanity check. Is the dimension working out correctly, which it should be fine. That's all that was. That was just more a sanity check here for me. I even should look, I'll just run that bit off there just to kind of show you. So you can just see here, look, that this is saying the matrix we're getting back should have 36. So when we're looking at the sizes, it should have 36 values, which is correct. And then over the 3 effect sizes. Okay, so the 3 columns. So then here's the outer loop. The outer loop is just looking at the increments of the effect size. So that's going to loop 3 times. Then the inner loop is very similar to plot 1 up above, which is looking at the power analysis. That's very similar to what's above. All that's different here is obviously the effect size, I suppose, reference is just is changed based on, I suppose, what effect size we're doing. And then there is the results too. Okay, so I'm just going to run that off just to kind of show that first. We end up with this table. Okay, so we'll come back to that table then at the end. Okay, so we end up with that. So it's very similar to what I would have done before. I'm just renaming it. Okay, when you look up here at the results, it comes out at x1, x2, x3. So I'm just relabeling it 0.248, 0.258, 0.68. Now, it's not that I'm a massive fan of labeling variables by value, but I suppose ultimately I know where I want to go with this with regard to the plot. So this was actually nearly the easiest step to do. And then I wanted to put it in a long format in order to do the plot, so I used the gather function for that. Then I plot the function by default, you know, the base, look what's my baseline kind of plot, and then I look at trying to make it fancy. So there are all the steps that I would have done here. Run that off, and here we get it. Okay, so that's quite nice, I feel. If we look at just maybe the similarity between this and the G power, here we are. So we can just see the red maps with the red, the blue and the green are just swapped around with regard to the effect sizes. But I think overall, when you see them there, that they are mapping quite well. So yeah, that looks good. So if we look at the table values again, we will see a bit of variation, but it should be at most one generally, and at most 2. So I'm just trying to find here, come up to result 2 is what I called it. Come to G power just to kind of see that. So I'll just look at 2 rows in this case. So if I look at the 0.6 to the first one, we're looking at, if we round this is 35. It's 35. And if you look at the G power one, that's going to be 36. If you look at the next one, then this is 33. Here is 33. This is going to be 30, and this is 31. So you can see that we're off by 1 again. And then if I just look down at maybe the 13th one, 0.72. So here we're looking at 44. 0.72. Here we're looking at 45. Here we're looking at 41. If we're looking at the middle one, we're saying 41, and we're looking at 42 here. And then here we're looking at 38, and here we're looking at 39. Okay, so there's that kind of similarity. I think if you scan through them, you might find one that might be off by 2, just because of just the way the decimal places lie. But overall, I mean, there's very good mapping. And again, that I suppose that slight deviation between them is not a surprise, given I suppose what the power analysis is relating to, which again is the between and within subjects design. And when you think of the work that you have to do in order to kind of get up to an ANOVA, to doing a between and within subjects design ANOVA, there's a lot of work, there's a lot of assumptions to be checking for, and so on, like that. Okay, as opposed to the pair t-test, it's quite kind of there. It's quite straightforward to get up to the pair t-test. You just have your one assumption to look for. So I think that kind of works out quite well. I hope you're happy with it. The one difference, I suppose, the big difference, I suppose, between this video and the previous one that I would have done on the power analysis is the power function that I used. Okay, the function that I used here is the web power repeated measures ANOVA. The reason I used that, just to reiterate it again, is I just liked the way it gave the non-sphericity correction, if that is something that you require. Okay, because you could find that you're doing a repeated measures and you're basing it on a Greenhouse geyser or the Hunfeld. I liked the way it did that, and also I liked the way you can focus on, I suppose one of the particular hypotheses is, and you can either focus on the between subjects or the within subjects or the interaction. So it kind of gives you that flexibility, which I think is a nice addition to the power analysis. And I suppose the other thing, just as a prelude to all that, what we actually had to do is we had to just do this, I suppose, convert our effect size out. There's loads of calculations out there. This was just a nice one that I found using SJ Stats library, so I thought that was quite nice and it was quite good to report. Okay, so that's where we are. Hope you find that of use. It's a big step up from the pair t-test, but I felt if I just went off and did an ANOVA one, I think you'd be able to figure the ANOVA one is kind of very relatively straightforward. That I thought I'd make a kind of a bigger leap up from the pair t-test to this one, just to I suppose, so we could just maybe, I mean, this is quite hard. I suppose I would feel like the between and within subject design, there's a lot to it, but hopefully you find it of help. And like always, if you do like this, if the video you found of benefit to you, then liking, sharing it is much appreciated. Subscribe to the channel, this YouTube channel. It'll be good because then you'll get updates on other videos that I'll be uploading. I'm going to do 1 or 2 more power analyses. I won't do loads, but I suppose the feedback on the t-test one was quite positive, that I felt, look, it would be worth doing another one, so that's why I wanted to do this. As always, there's more than one way of doing these things, especially when you're looking at RStudio. There's more than one function out there. If you feel that there's other functions that are maybe a bit more efficient than the ones that I'm showing, by all means, I love getting feedback, the comments, or you can email me or contact me at any one of these handles here, okay? But at the moment, sure, that's it for now. Hope you find this good, and we'll talk to you next time. Okay, all the best. Bye-bye.